Today's webinar is on RAG and Eval for LLM Success. You'll be hearing from 3 experts in the field who will start with an overview and then take you through a hands-on example. Let me introduce our speakers. Anupam Datta is co-founder, president, and chief scientist at TruEra. Prior to founding TruEra, Anupam spent over a decade as a professor of electrical and computer engineering and computer science at Carnegie Mellon University. Anupam and team have worked with transformer models since they were invented in 2017, and they have recently developed TruLens. It's an innovative open source project for evaluating tracking LLM apps. Prakul Agarwal is product manager for AI and machine learning at MongoDB, the developer database company. Prakul focuses on the MongoDB Atlas database and vector search. For joining MongoDB, Prakul worked in product and engineering at Zoox and Salesforce. And Daniel Huang is a senior software engineer at TruEra, where he focuses on machine learning research and developing the TruEra core platform. Prior to TruEra, Daniel worked in software engineering at Amazon, Lotus Flare, and Reflect. And with that, over to you, Anupam.
Great. Yeah, thank you, Margie, for the kind introductions, and welcome everyone. We're looking forward to the conversation today, and I'm particularly looking forward to tag teaming with Prakul and Daniel. You can try out TruLens and MongoDB Atlas. These can leverage the QR codes to get there. Here's a quick outline of today's webinar. We will begin with a quick intro to building and evaluating RAG apps, then go a little bit deeper into how TruLens and TruEra supports this task. Then we'll have a quick intro to MongoDB with a focus on the MongoDB Atlas vector search capabilities. And then we'll bring it all together at the end, walking you through a notebook where advanced RAG techniques and vector search, metadata filtering, some of these capabilities are brought together to build initially a basic RAG and then a more advanced RAG, and how the MongoDB Atlas search capabilities can help build better apps when combined with TruLens's evaluation and debugging capabilities. So with that, let's get started. I wanted to start with a very simple example. We asked this question, who are the founders of TruEra, of Claude 2 a few months ago, and this is what it came back with. And what you're seeing here is very representative of how large language models work, in that a number of the general trends here are accurate. There are 3 co-founders. The area in which TruEra works is also accurate, but a number of the specific facts are incorrect. They got my name and description right, but these 2 other co-founder names are inaccurate. Somesh is a real person and a good friend of mine, but Shayak Sen is our second co-founder, who does have a similar research and academic background, and similarly, Tomer isn't a co-founder, it's Will, and he brings some industry experience that is overlapping. With Claude 3, things have improved a little bit, and now Shayak is in here, but again, we have specific facts incorrect about him being a research scientist at NORAD and so on. And maybe with Claude 4, we'll get to Will. So one kind of key takeaway here is that as you start using LLMs for question answering, chatbot interfaces, the problem of hallucination is very central. And in some ways, that's what LLMs are trained to do. They're trained to generalize. And in that process of generalization, specific facts are not necessarily going to be accurate. with that recognition, the industry has moved towards embracing retrieval-augmented generation, as you know, where LLMs are not all that's used in a question answering system. In addition, these RAG-like systems augment LLMs with vector databases and search and retrieval capabilities to address precisely this problem of hallucinations. So in this workflow, if you have a proprietary source of data, you convert those into embeddings, put them into a vector database, and we will hear today about MongoDB's capabilities in this space, what's distinctive that is quite helpful in improving RAG-like applications and more. The LLMs still play an important role in this architecture, but they are now being used for the generalization-oriented tasks like generating embeddings, converting the original data into embeddings, converting the user questions into embeddings, and then in producing the final summarized response from the retrieved results in the query. But this architecture essentially recognizes the gap with LLMs, which is they generalize well, but they don't memorize well. So let's use them for general tasks and leave memorization to a different component to vector databases and retrieval methods. However, it does not solve the entire problem. Getting RAGs right is incredibly hard, and there are lots of different failure modes that we have seen in working with RAGs with tons and tons of users. When you are taking up that original set of documents or proprietary data and breaking it down into smaller pieces or chunking it up, converting into embeddings to put into the vector databases, there's a wide range of chunking strategies. And depending on which one you choose, you might get very different quality of results at the end. Data quality remains important. The embedding quality is incredibly important. So these models that are used to generate embeddings, there's a lot of choices there, and picking the right one is important. The search quality or the retrieval quality from the vector database has immense impact on the results. Query analysis, contexts can overflow, and this list goes on. In the final response, there can be hallucinations and so on. So what we want to talk about is ways of thinking about this app building and evaluation framework in an end-to-end way so that we are building with the right kind of primitives, as well as having strong evaluation capabilities that help surface these kinds of failure modes in a way that's actionable. You can improve the quality of your applications before you move them into production and continue to monitor and improve them in production as well. So with that, let me start getting a bit more into the TruEra capabilities and how we have approached this set of problems. Our work in this space has largely mirrored our view on how the world of generative AI apps was going to evolve from 2023 to 2024. In 2023, a lot of the attention was on prototyping applications, experimentation, and to build developer tooling that supports it, we launched TruLens in May of 2023. It's an open source toolkit for evaluating and experiment tracking for LLM apps that has started getting significant traction now. And in today's webinar, we will show you how to work with TruLens in a hands-on manner. In 2024, the attention has now started shifting from experimentation and prototyping to productionization. And so we launched a very significant upgrade to our AI observability offering that supports evaluation and monitoring at scale. And it's seamlessly connected to TruLens, meaning that if you started off working with TruLens, you can, with one line of code, start connecting to the full commercial offering which comes with additional elements of scale, security, governance, and so on. So these are the two resources that I'll point you to. We will focus in today's webinar on TruLens, which is our open source offering, so that you can start playing hands-on, you and your teams can start playing hands-on with evaluation, as you're building your applications. And then if you're interested, you can explore the commercial offering as well through our website. Before we start diving in, I would like to make things a bit more concrete. We have been talking about RAGs, and we've been talking about how they suffer from hallucinations. How do you evaluate RAGs to guard against hallucinations? One key concept that we introduced last year, which has gotten quite widespread adoption now, is what we call the RAG triad. The RAG triad very much mirrors the structure of the RAG, where the user comes in with a query, a set of contexts or chunks are retrieved from the vector database, which are relevant to that query, and then those get summarized by the LLM to produce the final response. And on each edge, there's an evaluation. Context relevance is checking, is the retrieved context relevant to the query? Groundedness is checking, is the final response supported by these retrieved pieces of context? And answer relevance is checking, is the answer relevant to the query? So these relevance evaluations are quite powerful to ensure that answers are on point, as well as the retrieved pieces of context from the vector database are truly relevant. And groundedness is particularly valuable to guard against hallucinations, because effectively what groundedness does, and you'll see it later as we dive into the notebook, for each sentence in the final summary, there's a way to trace it back to evidence in the retrieve pieces of context from the vector database that either backs up that sentence, or there isn't necessarily any evidence, in which case that's a hallucination. So we'll spend some time on these evaluations just to make things concrete and set you up, as well as your teams, to explore these kinds of tooling and capabilities. The RAG triad is a useful place to start. It's not all the evaluations. It's not an exhaustive list of all the evaluations. There's a broad set of evaluations that are available in TruLens out of the box that helps with ensuring that apps are honest and harmless and helpful. The RAG triad is in this honest bucket, but guarding against harm like toxicity, bias and stereotyping, adversarial attacks, and so on, are also other capabilities that are available that you can play with. One other interesting thing here is custom evaluation. So it's quite easy for you to add your own evaluations to the TruLens framework, and we find users doing that quite often. There's this abstraction of an evaluation or feedback function that we introduced, which involves providing a score after reviewing an LLM app's inputs, outputs, intermediate results, and metadata. The way TruLens works is that as you're building your Python app, TruLens is a library, you pip install it, you import it, and then with just a few lines of code, you instrument the app so that the entire execution trace gets logged. And then these kinds of evaluations are run over spans or parts of that execution trace. And that gives you very fine-grained, meaningful evaluations. One other comment that I'll make, and then I'll hand it over to Prakul, is that under the hood, TruLens and TruEra supports several different kinds of evaluations. We like to think of them in this kind of two-dimensional view, where on the x-axis is how meaningful is the evaluation, how reliable is it, how much can you bank on it. On the y-axis is how scalable is it. As the number of prompts and responses start increasing, how easily can you scale these evaluations and monitoring components. In practice, what we find is that it's useful to have this entire array of classes of evaluations. Often users, when they're starting to build their application, will start with ground truth evaluations with a curated data set where the correct answers are known, against which you can compare what's coming out of your application. Ground truth is high on the meaningful axis. On the x-axis, it's doing really well. On the y-axis, though, it's hard to scale this kind of ground truth data because it requires a lot of curation and expertise to do it right. So if you want to think of a concrete example in parallel, think about Morgan Stanley, for example, building their RAG and question answering system for their financial advisors. And the purpose of that application, and this is a public case study that came out with OpenAI quite some time back, the purpose was that when financial advisors are giving advice to clients, they can use this RAG-based system to ask questions such as, what's the house view on NVIDIA stock? And when the answer comes back, they can leverage that answer as part of and input into the process of giving advice. So when they started off with ground truth evals, which was a curated set of data. Once the application was rolled out in pilot mode to a set of financial advisors, then they started getting human evaluations from the users of the system, who were the financial advisors. So the distinction between these two buckets is that over here, it's the true experts who are creating these curated data sets. Human evals is coming from the users of the system, who also will often have domain expertise and will be able to provide feedback, thumbs up, thumbs down kind of signals, or even more detailed feedback. So they scale a little bit better than pure creation of ground truth, curated data sets. However, they're still fairly expensive to collect. Not everyone is going to provide that feedback, and there is often variance across different people. If you ask them the same question, you can get different answers. So we are starting to get a little better in terms of scaling, but it's still very manual. So where we see the path to scalability is up here through programmatic evaluations. And programmatic evaluations for large language model-based applications, a natural place to start is with traditional NLP evaluations like BLUE scores and ROUGE scores. And that's a useful weapon to have in your arsenal. However, they do have fairly significant limitations in terms of being meaningful because they're quite syntactic. So if you think of a summarization use case, you have the full document, and then you have a summary that's generated by an LLM. If you use these kinds of metrics, it's going to look for overlap between words or tokens or sequences of words between the final summary and the original document. And because the summary might use different words, it might be semantically similar, but syntactically, the specific choice of words could be quite different. And because of that, these metrics tend to have false positives and false negatives. On the further right, we are starting to get to new kinds of evaluations, leveraging the power of large language models, where a GPT-4 model or a Llama 2 or 3 model could be the basis of creating evaluations. And with LLM evals, the key trade-offs are that on the positive side, the benchmarking that we have done, but also there's a wider body of research in the community now, shows that LLM evaluations have strong agreement with human evaluations. So if you look at the x-axis here, they're about the same. There's an interesting paper that came out from a group at Berkeley last year called Judging LLM as a Judge. And part of the finding there was human-human agreement is between 80 to 90%, and LLM eval agreement with human evals is also in the same neighborhood. So that kind of indicates that on the x-axis, we are starting to get good results with LLM evals. The downside is that they can be quite expensive and slow. LLM evaluations can work reasonably well during prototyping and experimentation, but in production use cases where the volume of data goes up quite a bit, in those settings, it's important to think of other ways of getting comparable evaluations. And some of our results show that smaller models that are specialized and fine-tuned to do evaluations like the RAG triad around groundedness, context relevance, and so on can be quite promising in that context. So with that, let me now hand it over to Prakul to provide the background on MongoDB and MongoDB's Atlas search in particular, and then we'll transition to Danielle to get into the hands-on notebook. Over to you, Prakul.
All right, thank you so much, Anupam, for that insightful walkthrough. Let me pull up my screen real quick here, and we can dive into some of the steps required. All right. So as Anupam mentioned, building RAG applications are very promising, but also complex process. And it's very much iterative in nature. So with MongoDB, we are a developer database company and have been building tools and products for storing data and using them in better ways. So for MongoDB, we had an Atlas vector search in private preview much before ChatGPT became public and vector databases as a category grew that limelight. We have had customers starting to build things with us on many innovative use cases, and we became generally available last year. So the way we look at how the vector databases and how it works in conjunction with all the database platform requirements is just by having an integrated semantic search along with your operational data store allows you to build intelligent applications like RAG much quicker. So when you're able to store your vector embeddings right next to your metadata, first advantage it gets you is as that underlying data or metadata changes, MongoDB's vector search is able to keep things in sync without you having to put in any additional layers for ETL as your data changes, right? So it's automatically synchronized to the vector index. Thirdly, like now, as you are ready to scale things in production, we have something called search nodes, which allows you to transparently scale this integrated operational and vector search into its own separate instances, such that you're able to optimize your resource consumption by putting vector search on a specialized hardware, improve your performance, as well as your availability. So overall, building with MongoDB, these RAG applications allow you to iterate faster, get into production quicker, and be assured that you have your operational heavy lifting is being minimized. You're focused on your core business logic. So the way we look at things, right? So just to elaborate on the point of the two paradigms of building these RAG applications, the one on the top right is having a separate vector database, right? So this would require you to have your own operational store where your application is being powered by, then a vector store, and you have two separate query languages, and you are responsible for building this ETL logic. Like a lot of our customers struggle with that, and that's been a big reason why you move to the architecture on the below, which is having database with integrated vector capabilities or natively. And we'll talk about how this helps you iterate on RAG capabilities that Anupam mentioned. And the second piece to that is in conjunction with how you put your data is your ability to be able to use composable queries that come with having a full-fledged data platform. So there are these interesting possibilities that become available when you're able to combine your vector search queries with other kinds of queries like inner joins with the traditional stores or aggregations, and be able to get this in a very much operator push down manner such that heavy lifting is being done by the database rather than you in your application code. So just a few examples, right? One of our big customers is using geospatial search combined with a vector search. So suppose you had a query that you wanted to power, like recommend me restaurants that match my taste only within 10 miles of my current location. So LLMs are great at being able to understand your preference and recommend restaurants from a given data set, but it would not necessarily work great for some specific extractions like, okay, 10 miles from your location. So that's where having this rich set of capabilities come in handy. So now we just want to talk about some of the advanced RAG techniques and how having this tight integration loop between making changes and capturing evaluations from those, so that you know that you have a more of a test-driven development approach where things are going hand in hand, you're sure that things are moving in the right direction, and you're tracking them in production if things change. So in that RAG pipeline that discussed earlier, there are these two paths. Like one is when you are indexing your data. So you take your private knowledge sources, you put it into indexing step, and you store it into a vector database. And on the query path, which is elaborated on the left below, is when a user comes in with their query, you would put it into a pre-retrieval process, extract your knowledge from a retrieval source, and then be able to like put it to a prompt, pass it to an LLM, get your results. So I want to talk about like all the knobs and whistles that MongoDB allows you to experiment with from a retrieval perspective. And we'll talk about how you can evaluate each of those changes using TruEra's offerings. So from powering the memory for any RAG applications, the core construct is that of vector search. You want to iterate, go a step ahead by combining vector search with metadata pre-filtering, where it can work better on certain use cases. Further down, in certain cases, you benefit from being able to use vector search with some post-filtering capabilities, whereby a pipeline can retrieve results by a vector search and be able to do aggregations on it. There are also cases where instead of relying on an embedding model, you can benefit from a more traditional text search, such as that powered by a BM25, especially on some of the out-of-the-domain queries where the embedding model may not be trained on that kind of a data set. And finally, there is that possibility to combine your pure embedding-based search with these more sparse search, like a text search, use of this hybrid search capabilities. So with all these different steps, as we said, it's important to iterate, but also to measure. So just to give some context on like, why exactly a pre-filtering capability will help you improve your RAG performance than just a pure vector search query. So let's say we have a movie data set, which has a bunch of these fields. And now the query that we want to do is there is a plot that talks about all the different things. And we're trying to figure out, give me some like comedy movies with imaginary characters, but also like, I only want to watch movies in 1980s. So you can take that entire query, pass it onto a vector search, and just be looking at the plot field. But if essentially not considering the metadata that you already have in your data sources, which is your year of when the movie came out. LLMs may or may not be that great with reasoning on when the year came out. So you have the ability to split the query that the user originally asked into two separate queries where you can extract the pre-filters. And pre-filters will be powered by an exact date search that MongoDB provides for, such that you're able to get a subset of these results, a subset of this graph, which is only movies in 1980s and 90s, followed by doing your vector query of two comedy movies, like, just case two here, comedy movies with imaginary characters. That's where your power of large language models are being leveraged to get to the final result set, which follows all the criteria. This is different from using a post-filter step where your initial query would have been a vector query, which would be give me all the movies, comedy, and have imaginary characters, and then doing a post-filter step of giving movies between 1980s and 1990s. In this case, what we see is a different result set from what we got earlier, flipping the order of operations. And this is a sparser result because our vector search query, based on embedding model, got other movies which were not in 1990s and 80s, resulting in a set which was less than what would have intended to be. So those are the ways you can think of like pre-filtering, post-filtering, and how it leads to different results. And finally, we just want to talk about how would you combine your text search and your vector search with using hybrid search. So essentially with that same data set, you would enable two separate indexes in MongoDB with one for vector search, one for text search. And each query that you ask is essentially routed to do these separate indexes. Now, based on the scoring that you define, you would want to experiment with fusing how much emphasis is paid to the text search and how much emphasis is paid to the vector search. And based on that, be able to combine these two separate lists into a single coherent list, which will get you to a different kind of capability. And typically, we find our customers in certain restricted domains to be much more successful in using this technique than just a pure vector search capability, for instance. And again, there's a big role of evaluating each of the steps that we are taking here that we'll cover later. So just as a grounding example, we talked about the flexibility of modeling, that like what having the integrated vector embeddings with your metadata and your source data can do for you in the beginning, right? And so this is what a sample document looks like in MongoDB. You have your all the data, your source, your quarterly information, and then you add on embedding to this document. With the flexibility, you can have multiple embedding models in your testing pipeline that you can be adding into the same document. With this, you can also add, for instance, metadata that you may use an LLM to extract from this data that you already have, add on to that. And MongoDB is able to take care of all the requirements for scaling and that your query times are not suffering. Once you have this, you want to evaluate different chunk sizes and what impact it has on groundedness, and you want to impact on retrieval performance with embeddings. Define an easy vector index definition that specifies, in this case, the number of dimensions for the embedding model you're using, your similarity scores, as well as your path on which it's lying. And once you're ready to actually, so this index definition is just for pure vector search. And whenever you're ready to add a metadata filtering to it, you just modify your index definition to also include a secondary field on which you want to filter by. Once you define this, there's no operational load required. MongoDB will take care of making sure your secondary indexes are built and you're able to start querying these in the same syntax that you had earlier by just adding on to this metadata filtering. Basically, no sync required. And just briefly want to talk about the syntax, all the hyperparameters that you have available for doing this filtering, so that there is a stage called $vector search, which allows for specifying a filter, which is a pre-filtering construct. There is a limit, which is the number of neighbors that you want to return. And there is the number of candidates, which is kind of like these HNSW entry points that you want to explore. So essentially, your data is set into different segments, and you can request from different segments, fuse them together. And then that's what num candidates allows you to do. And HNSW is the algorithm for, which is called it hierarchical navigable small worlds, which we use for doing this kind of approximate neighbor search queries. And again, there's a lot of rich syntax capabilities that you can improve for improving your RAG. So in this case, we just want to talk about different pre-filtering options: less than, greater than, less than, not in, and etc. And allows you to put together really powerful constructs. So in this example, we are doing a pre-filtering based on AND construct that the data set should only be in certain fields in an array of certain options, but not in an array of second options, such that you can filter it much more effectively. And with that, let us get into the section
Maybe before you dive into that next section, Prakul, if I can ask a couple of questions.
Yeah.
And make a couple of comments, and maybe stay on the previous slide, and then we'll get into. So what seems really powerful here is the ability to, there are a couple of things, right? One is the combination of the hybrid search, the combination of the search in the, or retrieval in the embedding space combined with full text search, right? And then there's also the specifics of how you do it with metadata filtering. I wonder if you're able to speak to a little bit the impact of the expansion from just pure vector search to the hybrid setup on, customer use cases or types of use cases where you're seeing this being particularly valuable.
Yeah. So I think one kind of an industry which really benefits from this is if you had, let's say, if you're a medical company which is in insurance space trying to process a lot of the documents from various providers. So just for doing, and this is a kind of a hypothetical scenario, but also not so a hypothetical scenario. So company building a RAG applications for powering its frontline staff for being able to provide answers to providers and customers. So doing a query set on things like, give me all the medication recommendations for diabetes, which are generic in nature. So now they had certain requirements around what embedding models they can use, and it has to be on-prem, it has to be regulated in a certain way. So what this RAG applications was coming back with was essentially all the cases where the diabetic patient can be like provided insurance coverage. The reason for this was in the source document where the diabetes and generic medications were mentioned. It was also close by where all the information about how diabetic patient intakes work. So that's where like a lot of the data modeling goes into picture, right? Like you want to, how the chunk size you picked and the chunk size you picked and how it was ordered included information about generic medications with the information about how diabetic patients should be intaken. And in this case, the embedding model that was used did not had a very high semantic similarity overlap between diabetic medications and diabetic intake procedures, and did not understand that well about generic medication, nature of generic medication, how it's different from a like prescription and proprietary medications. So in this kind of a scenario, being able to go from a pure vector search to using LLMs to extract some of this metadata, tagging each of those chunks on if it is talking about patient intake information or medication information. So now you have that metadata that's added onto the chunk that was not originally present as a first step. And secondly, being able to combine with rich capability, we are able to do much better retrieval.
That's a fantastic example. And that's also highlighting where the state of the art in this field is, in that the embedding models are not perfect. And in some ways, like down the road, you might expect that maybe the large language model based embedding generation process can improve enough that these kinds of semantic concepts are also captured. But certainly we are not there yet. And having metadata separately for filtering and search just adds a lot more reliability to the process. And we see these failures of retrieval a lot in our experiences as well. So yeah, thank you for sharing that. And there's a bit of couple of questions that are coming in that might be good to answer for you to answer before we switch into the notebook session, which is RAG doable with PyMongo?
Yes. So there is this vector search construct that we provide is available as a syntax in PyMongo, as well as other language drivers that we have. As always, you would be using some other embedding model that you are expected to. So the vector search takes in the query vector. We don't provide support for embedding our models or any of the developer toolings around that. So that sits outside of PyMongo.
The other quick question is the Mongo vector search available outside of Atlas, for example, in the community edition?
So it's not available in the community edition, but it is available in the Atlas CLI, which allows you to bring up a single node on your local workstation, laptop, wherever, and be able to run all these queries, etc., for your development workloads.
So there's a way to get started for free.
Yes.
Through that.
Yeah, there's a way to get started for free in a air-gapped local environment. And also when you're ready, move this to Atlas. Atlas also provides a free, always free tier that's pretty generous. You can do a lot of your use cases with just the free tier forever. So yeah, there's a path on local to kind of path.
Great, awesome. I think that also we have now answered all the live questions. So let's also take this as an opportunity to transition to the next section of the webinar, and over to you, Daniel, to bring it all together.
Yeah, thank you, Anupam. Thank you, Prakul. Cool. Yeah, so let me share my screen. And then I know this is a webinar, but I would love to have this session, to be super interactive. So feel free to interrupt me during the process. I will try my best to pay attention to the live chat section so that we can, sort of like going through this together. Yeah, hopefully my screen now on the slides are visible. So yeah, after the introduction of MongoDB and TruLens, TruEra, so want to take a quick a moment to say like the following notebook, we have a QR code you can scan. This is a collab notebook link. Feel free to glance over it. There's no need to directly run it. It should be runnable, fully runnable end to end. But I will walk through every cell individually, and then kind of like talk through the details tie back to the previous
Daniel,
post.
I don't see your screen.
Oh, let me try again. No webinar is complete with some technical hiccup here. Sorry, bear with me a moment. Get my tab oriented.
Now, do you want to stop and try again?
Yeah, I wonder if we lost Daniel.
Yeah.
Are you back, Daniel?
Yes, I'm back. Turned on my Zoom. My Zoom directly crashed. So yeah, there are two me in the section. So there's like doppelganger, but let me try again. Is my screen visible now? Hopefully that is.
It is, yes.
Yes.
Thank you. Awesome. All right. And the slideshow hopefully is popping up.
Yep.
Cool. Yep. So like I said, this session is meant to be hands-on for me, acting as a voiceover. So a quick refresh. Want to talk about the RAG triad. So the RAG triad is a construct that helps us evaluate a RAG system in an end-to-end manner. But what really we found it empirically makes it really powerful is that the ability for us to drill down to different components in the sort of like a lifespan or sort of like a life cycle of a request into a LLM systems nowadays. We find that to be super valuable, especially a lot of the LLMs nowadays, when we talk about them, they are not just a model, right? They are not just a input in, output out model. They are a lot of time, they are API, they are guarded behind the API, they are a product. So there's a lot of sort of like transparency or visibility or even explorability, observability that we try to inject during this process. That is fairly hard to do if you just look at, let's say, a GPT-4 Turbo API. So the RAG triad provides sort of like a framework for us to look at three different main components of a LLM request. So first, we have a user query, like Anupam mentioned. The user query is just, most of the time, it's just the users asking a question. A lot of time, it could also include like system prompts if we have been playing around with a lot of different LLM type application or data type applications. The context, it's where the RAG, this particular framework, retrieval-augmented generation framework, particularly focused on is to perform retrieval from your custom data sets or your private database. A lot of time, these databases are vector databases, but like Prakul mentioned, MongoDB bridges the gaps between a traditional operational database where you might already have a lot of your metadata accumulated for the past several years, and then we directly inject the embedding model into those product offerings so that you can retrieve the context not just by keyword, sort of like in a keyword search manner, but also by semantic search manner. So semantic meaning, let's say if I ask a question about what is an apple, right? Semantically, it could mean the fruit apple, or it could also mean the company, right, in the Silicon Valley or in the United States. So this is what this context in the RAG triad really means. It's a retrieval, retrieve chunks from your DB, whatever that DB might be, very well be MongoDB or in an Atlas cluster. Finally, the response, this is typically what most people just associated with a LLM output, right? The LLM gives you a response. But this response in the RAG architecture, they are actually just a final step of the generation. The LLM takes in the retrieve context chunks and then try to reason around it and then piece together a hopefully well-informed and then grounded response. And then finally send it back to the user. So in all these three arrows right here, these are the three pillars that we are going to be looking at in our TruLens notebook today. The context relevance, just as a quick refresh, is to evaluating if the retrieve contexts are relevant to the query. So you could have a correct answer, but during the retrieval process, meaning the interaction between your database, between your vector database, between your Atlas cluster and your collections, the retrieve context might be not so relevant to your initial question, but still the LLM, because of the pre-training nature, because of all the web text it has been pre-trained on, or all kinds of custom data has been fine-tuned on, it is somehow able to reason and then provide a plausible answer. So this is a case where you will be lacking in context relevance, but still be given a very relevant response. So in the notebook that will soon to be seen, we might have very high score or high evaluated sort of like quality in answer relevance, but still having a relatively low score on context relevance. And then finally, the groundedness is something we'll be focusing heavily today, because groundedness really is something we find it very critical and instrumental to preventing or mitigating hallucination. Groundedness here means, is your response, like every statement in your response, supported by the retrieve context? So you could, like I said, you could still have a correct answer, seemingly correct answer, but maybe it is not retrieving the correct pieces. And we will soon see how that could happen. All right, so let's get to the hands-on walkthrough. Feel free to just interrupt me if I'm going too fast. So let's head to the notebook. Hopefully the font size is good. If not, just give me a shout out. This is the same link that we provided in a QR code. This is a Atlas Vector Search Quick Start notebook. First, There's nothing out of ordinary here. You just install using pip or any kind of package manager that you want. TruLens eval. We use Llama Index here as an orchestration layer to help glue together all the different components in a RAG architecture. But in reality, you could use any type of orchestration layer like LangChain, or you can even just use different type of APIs in your own system. You are not necessarily tied to Llama Index. Now, the first step is to just having a one-line import of TruLens, and TruLens will be able to use starting your DB locally using SQLite, or you can directly connect your database to your existing instance. So any type of relational DB will work in this case is to store the metadata or the records generated by TruLens. That is the evaluation result. So here we first reset the database, and then we will soon head to the UI later to look at what the database actually look like, or the evaluation UI actually looks like. For all the imports, we just here nothing out of ordinaries. In the live chat previously, people asked about PyMongo. We are using PyMongo here to connect to our LS cluster as well. And the only credentials here we'll be using today is the OpenAI API key and also a LS connection string. This helps you with my credentials. This is a free tier example, like Prakul mentioned. This is a one of the I think like single instance cluster that is hosted on Atlas. We will also probably, if we have time, we'll probably visit that UI for a brief moment. Now, the important part here is that embedding model in the RAG, sort of like end-to-end RAG system, actually matters a lot for the RAG quality or retrieval quality. So here we are using, just for demo's sake, we are using OpenAI embedding, but like Prakul and Anupam mentioned, we could use any type of fine-tuned or custom embedding model if you find it works better. And how do we know that it works better, right? So this is why we always say eval is all you need for a lot of times. Now, the sample data we'll be using today, we have 3 fairly long, extensive documents or data sources. The first one is Atlas best practices. This is a PDF file of about 20 pages. And the second one is a very dense document called DB Essential, published in 2021. The last time I checked, it has more than 121 pages. And they all fit in a free tier Mongo Atlas cluster. So yeah, so these are all being converted to embedding. The final one is a short document. It's called Vector Search. This is a course from Databricks. So we can quickly take a look at what I meant by, oops, let me orient it here a little bit. Yeah, so this is a DB essential. Like I said, this is super long document, 112 pages. And we have this short presentation. This is just a discourse or a course on vector search, similarity search, semantic search, super relevant to our today's topic here. Yeah, so that's it, all 3 of the documents. We loaded it up, and then we converted to embeddings. So the first step you will be doing is in Atlas UI, we will be creating this vector search index that we are just gonna call it vector index, I believe. The most important thing here is the path. Like Prakul's slides previously, I can go back there real quick. Sorry about the jumping through the slides here. Yep. So this is how it looks like being after created. I just want to have a better presentation here. So the path, like in the Prakul's previous slides, the path here actually can be any metadata or fields of the MongoDB document model. So here we are using a metadata field called file name. We will soon to see why it matters. This is a vector search index you can easily create in Atlas in 2 steps. The search index is named vector search. Give it a moment after it's created. I already created in my cluster, so I have a screenshot below. Notice we have a embedding dimension that need to match our embedding model, because Mongo Atlas also support different embedding models. So depending on the embedding model you use, you might have different dimension. here we have 1536, which is the OpenAI embedding model like we saw in the beginning of the notebook. Keep going. We have a MongoDB client to connect to the Alice cluster. Then we actually instantiate a vector store. Like I said, the index name here need to match what you created in the Alice UI. That we just name it vector index. And then here I have a MongoDB database called Alice Quick Start Demo. The collection name is test. We initialize it as a vector index. Vector index in itself is just a data structure that helps you retrieve, in a super fast manner, depending on the algorithm you use, retrieve similar vector embedding. Now we started out a basic RAG. This is using llama index. Like I said, you're not tied to the llama index here. This is just a syntactic sugar that helps you create a query engine. In a LangChain, people might call it like a chain or something like that. It's a callable object that you can just directly call with your user input. So effectively, you can do query engine.query and then add a user questions. Boom, you will get the answer from the end-to-end RAG system. So this still is what really matters in sort of like the crust of the evaluation triad of TruLens. So remember, we have the triangle. We have 3 different metrics we want to evaluate, or 3 criteria we want to evaluate on. So first one is groundedness. The second one is answer relevance. The final one is context relevance. So these are the lines of code you would need to get your entire app instrumented using TruLens for any type of really like any type of end-to-end LLM applications. You can use any type of model. It can be the model provided by AWS Bedrock. It can be OpenAI models. It can be open source model from Hugging Face. These are all you need. And then people might ask, there are so many different type of LLM applications. There are so many different type of shapes of the models, form factor of the models, even like form factors of the API calls. How will we be able to kind of like instrument it all? So here we adopt an approach that's super flexible. It essentially inspect the architecture or the structure of your application, and then it looked like the output or input and output both, or input and context. So you can see here the syntactic sugar here is where we really help folks like having an abstraction layer that you can directly tie to different components or different spans of your application, for the folks who are very familiar with the open telemetry world. So we will soon see in TruLens in action to see how we actually select these different components. By components, I meant the input to your application, the final output, or the intermediate context, right? Because a lot of time, in order to have a good comprehensive evaluation, we need to be able to also look at the retrieve chunks, like what we had seen in the
and maybe I'll add a couple of sentences here, Daniel, in response to some of the earlier questions as well. So there are some questions about comparison with other open source evaluation frameworks.
Sure.
And one area where we have spent quite some time architecting it in a with the right kind of general abstractions is, an instance of which is what Daniel is showing right now, is that our architecture in TruLens is very much, it's inspired by some of the work in programming languages called on bidirectional lenses. And the key insight there is you want to have a very general framework for, because if you think about these evaluations lets us do fine-grained evaluations by focusing in on parts of the overall execution trace, the end-to-end execution trace, starting not just prompts and responses, but intermediate results in kind of fine-grained controlled way. So we have these abstractions of spans over traces. A span you can think of as a part of an execution, and then lenses or evaluations, which let you zoom in and focus on that part. So if you look at the context relevance one in particular that Daniel now has his cursor at, that is making use of the initial input, the query, that's the dot on underscore input, and then the intermediate set of retrieved contexts from the vector database. So that's the span for this evaluation. For answer relevance, it's the query and the final response, the initial query and the final response. For groundedness, it's the final summary response from the LLM relative to the set of retrieved context. So they're looking at different spans, if you will, of the overall execution trace. And because this abstraction is done in a very general way in TruLens, it lets us also do the instrumentation for different app building orchestration frameworks. So this particular notebook is with Llama Index, but there's a very similar instantiation for LangChain. And then more recently, we did some work with Pinecone. They have an open source framework for building RAGs that they call Canopy. And I'd done a different webinar with them. That's also available online, so you should be able to look it up. But as we went from LangChain to Llama Index to Canopy to just other custom Python frameworks for building RAGs, TruLens kind of carries over very seamlessly because of these abstractions of spans and of traces, spans, and lenses. And that is a big advantage over some of the other frameworks for evaluations that you might be familiar with. The other piece that I'll add, and this is true both of TruLens and of the MongoDB approach, and I'll let Prakul perhaps elaborate on it, is that we are not building an open source project in isolation. It's very closely tied to a scalable production grade commercial offering that you can scale up and down as needed for use in your companies and enterprises. And while this webinar, we are not spending much time on it, that end-to-end view is very important, because otherwise there's just this risk of only staying in the experimentation mode and prototyping mode. You can build cool apps over a weekend, which is a useful starting point, but having that end-to-end production grade system where you can start off in open source and then transition into the full enterprise grade scalable offering requires a different kind of first principle thinking that we have been thinking about from day one. And I'm sure Prakul, you might have more to add on that as we go along.
Yeah, I think just to add on very quickly, right? So just starting from your notebook, your local environment, putting it into production, testing it out, putting into scaling it out to all the customer bases. There are these different requirements, and it's kind of essential that each of these things scale with you. So for instance, for some of our work with TruEra on this, it's local open source works great, but that you're helping in terms of understanding the choices on how you want to model your data, how you want to ingest things, what embedding model, what chunking strategy. But also as you put your application in production, you want to make sure firstly your vector database scales, but also your evals are able to act as that front line with your customers as they interact, and able to give you the visibility on how your systems are performing so that you can fix things, but also continue improving over time. So I think that's really kind of the critical piece. And a lot of these abstractions are flexible, but also easy to get started with, right? That's the philosophy that we have with MongoDB, developer experience at the very core of it, but also a lot of the power under the hood that you want to customize and continue building on in an iterative fashion. And I think that's super important for putting things in production.
Yeah, thank you both. And then just quick point to follow up what Anupam and Prakul said. So two quick things. So we have over I think about a dozen or 2 dozen of quick start notebooks with different type of integrations for different orchestration framework that you can try out. And we also have the the most custom mode that you can just instrument your application if your application is in none of these framework. So feel free to take a look at our open source GitHub. The second thing is that I think the TruLens is one of the or two of the main pillars, or two of the main the goals we had in mind when building these tools are, first is high level abstraction. So like Anupam mentioned, It helps you have super high adaptability and flexibility to different application structure, different form factors, the LLM application in particular. And the second one is scalability. So tying back to the sale right here, we haven't actually talked about how we are evaluating, right? I saw the questions about, there are folks asking about how is it like different from RAGs, right? A lot of time, people use another set of LLMs to evaluate your LLMs. And then it turned out to be like all kinds of like fairly hand-wavy prompt engineering, right? Because the other LLM can also have all those non-deterministic nature. And right here, I want to look at zoom into the code here to mention these. The reason we call them, we have a prefix F is because these are all what we call feedback function. Feedback function is the core of our abstraction. Feedback function in itself, you can view it as just a function. You give it any type of argument, it will output a scalar score. So people might think, oh, is it like you just prompt a model and then ask it for a score? It could very be that case. For remember the 4 quadrants Anupam had, it can be fairly scalable, barring some inference costs on those models. Like we had for the demo purpose, we have GPT-4 Turbo right here as our feedback function or evaluation backbone. But nothing stops you from using your own model or even an enterprise grade ready custom model to have lower latency, faster speed on evals itself. So not only your application need to be scalable, not only your data store need to be scalable, the evaluation itself need to be scalable so that it can be used in a very high, like latency sensitive use cases. Think about like guardrail. Guardrail meaning you have some feedback mechanism built in during the output time and then happening almost real time alongside with your application. In those cases, these feedback function, we can easily in TruLens swap out the backbone to have custom model, open source model, even modelless approach, if you will. It could very well be some custom algorithm that we build at TruEra or you build yourself, and then the framework allows you to just plug in and play with that, and then having a very scalable way to zoom in and zoom out using the lens's mathematical construct. Now, so here is a quick example.
Daniel,
yes.
There's one other question that, if you don't mind, I'll answer while you stay on that screen with the definitions of the feedback functions. Yeah, scroll up a little bit so groundedness is visible as well.
Mm-hmm.
Right. So the question was, why does groundedness use context.collect, whereas context relevance just uses context? And the answer to that is that these evaluations are doing somewhat different things. For context relevance, what it's checking is, let's say you ask a question, and Daniel will give some examples very soon. So this will become even more real as he walks through the demo and through the notebook. But let's say you ask a question like, so your examples here are related to, say, databases, right? So let's say the question is about columnar databases or something like that, or okay, let's pick that up from here. Yeah, what is the impact of interleaving transactions in database operations? So when that question is asked, let's say 3 pieces of context are retrieved from the vector database, and then those are summarized to produce the final response. Context relevance is checking for each of those 3 individually. Is this context relevant to the question that was asked? That's why it's looking at each context separately. So F context relevance just uses context. Groundedness, on the other hand, is checking for the final answer, summarized response coming out of the LLM, for each sentence in that final answer, is there supporting evidence in the union of all 3 retrieved pieces of context? That's why it's that collect option is what it's doing, is that it's looking at the combination, the union of all 3 retrieved pieces of context to find the supporting evidence or lack thereof. So that's the reason for it. And then the aggregation step is, for each sentence, you have some evidence, you get a score. So let's talk about groundedness. The aggregation and groundedness is, for each sentence in the final summary, you're getting a score of how well grounded it is. and let's say there are 4 sentences in the summary, then for each one of them you get a score, and then you aggregate it in some way. Could be a average across all 4.
Cool. Yeah, and let's probably it'll be easier to see actually all these things in action, right? So yeah, so these are just the instrumentation steps, takes you to the internal of the app to show, sort of like instrumentations we have put in places. And here I just directly have a dry run of the feedback function to show what that really is. So if I run the context relevance with a made up example, what is Apple? And the second part of the arguments is actually the context. So that's why we say about the flexibility, right? The feedback function construct need to be able to take in all different type of arguments in all different places or even different times of your entire trace or your LLM request lifecycle. So in this case, the second piece is a single context, like Anupam mentioned. So this F context relevance feedback function is evaluating how relevant the second piece is regarding the first piece. Now, it gave a point about 0.2, but the most important thing is about the reasoning, right? The feedback score is between 0 to 1.0. So it's saying like just eyeballing, we might see this is somewhat relevant. So it shouldn't be a 0, but it shouldn't be too high because it is mentioning orange. They are both fruit, but they didn't give us like any intrinsic expectation or characteristic of an apple, right? So that's the reason being mentioned here. So that's just a quick example, like you can do a single out run of the feedback function and see what it's actually doing. Now, all these 3 lines, the final line here is all you have to do to wrap around your application. Here we have different type of wrappers designed for, like we said, different type of orchestration framework, different type of application type. Here the query engine is a Llama index query engine, so we wrap it with TruLama. Now you have your full app instrumented. Now we can see that in action. Here are the test sets or test cases. There are a few questions. There are 2 questions I wanna kind of like dive deeper. I purposely choose 3 documents so that in all the semantic search space, it's pretty wide, and then we all know about these documents are somewhat related. It has best practices on Mongo LS. It has DB Essential. Remember the 112 pages, super long PDF. So searching like a needle in a haystack here, retrieval is fairly difficult if it is not able to retrieve the relevant context. And then finally, we have the third one from Databricks called semantic search, and I ask a question about what is fast. All right, so 1, 2, 3, 4, 5, 6. There are a total of 6 questions. Now, testing time. So this is all you have to run. This line is what we are asking the question. The test prompt is just corresponding to all the questions above and getting the evaluation result. So finally, we have a leaderboard. This is just an aggregated result. So what might be more helpful is actually head toward the TruLens actual UI. So let's take a look. We have now I named the application basic RAG. So the application here is basic RAG. And I want to show how iteratively we could improve that. So please focus first on this app ID basic RAG here. And then we have some scores on the right-hand side. These 3 other RAG triads: groundedness, context relevance, answer relevance. So we have a leaderboard because I already did several runs. So the basic RAG right here, we can see, very jarringly, we have relatively low groundedness and also pretty low context relevance. And then in the second V2 iteration, I drastically improved the groundedness. Let's see how they actually perform the instrumentation and improvement. So if we look at basic RAGs, see here are all the questions corresponding to the 6 questions I mentioned. These are the responses given by the LLM or the entire RAG system, so to speak. If we look at, let's say, what is FAST or FICE? Nobody knows how to pronounce it. But what this stands for is Facebook AI semantic search. So if we look at the low groundedness score, you can see all 3 scores are being listed here. Here is what Anupam mentioned, the view of an entire trace, meaning the life cycle of this entire request. All these different tabs here are components. So we can take a look, zoom in into any of the nodes. We can even just view the embedding itself. The embedding itself are just floating points number, so it probably wouldn't mean much to the human eyes, but the return value, right, the text itself can be very, very insightful. So let's pick, maybe we are interested in the context relevant first, right? So let's look at the question, what is fast? And then the answer is, we are given FAST stands for Facebook AI Similarity Search, which is actually correct. This is not like surprising because FAST is fairly well known, so we can assume a fairly powerful LLM already knows about that. But what about the context it actually retrieved, right? So if we click into here, you see this closure mathematical formula here. This is actually nothing related or relevant to FAST. FAST is something being mentioned here in my Databricks courses. So this is the third document that we imported, and then we converted it into vector. So it wasn't able to retrieve anything related to list slides particularly. Then if we go to the retrieval chunks, we might be able to see what is actually retrieved, right? So in reality, we see this is being retrieved from a different model, actually. I believe this is not being retrieved. This is a little hard to see, but yeah, so right here, we can see the metadata, and then we can see, file path. It is actually retrieving all these embeddings, but from which file? From a super long PDF file called DB Essential, right? So this is not the right document we want to perform a retrieval, even though the answer is correct, which explains why it gets a 0, actually, very hard score, right? But a 0 score on context relevance. Now, the answer relevance is perfect because, sure, it answered the question in a very relevant way, even more so, like it's actually correct. Groundedness, very similarly, we can look at why groundedness score is 0. Now, this is where the power of TruLens really comes into play. You can see all the sources and you can see all the reasons. There's nothing found for supporting evidence. And this is because, like we said, this closure, this mathematical formula here is not related to FAST at all. So we should do better, right? So let's head back to the notebook. How can we improve some of the groundedness metrics? And in reality, if we take a step back, if you look at it, why is my RAG system not performing up to the center? Hey, we know we have 3 documents. Some of them are super long. So the search space for your vector DB, even however well you have your indexing scheme set up, it's fairly hard to perform sort of like a needle of a haystack retrieval, right? So how can we do better? The second round, we want to do something called metadata filters or pre-filtering, like Prakul mentioned. We noticed for that particular question, I asked about Facebook similarity search. It actually looked at the incorrect documents. What about before we perform vector search, we perform pre-filtering using the power of traditional databases or information retrieval capability indexed on a metadata called file name. This is exactly what I did here. I have 3 different metadata filters, each attached to the 3 different documents: DB Essential 2021, Mongo Alice Best Practices, and then finally Databricks Vector Search. So with that, we have the power of metadata filtering. Then the second one, we will have a different router engine. So this is what we call router query engine filter v2. Now, do another run with all the query question using the same set of 6 questions. We check the results. Again, this is a leaderboard. We can also see that on the top, we see groundedness improve drastically. But what does that mean? This is an aggregation result, right? So let's select the app, go into this particular filter application. I want to zoom into the same question so we see how differently it performed this time. So you can see the app ID is router query engine. There's a little hard to see here because of the column, but yeah, this is the filters v2 with metadata filtering. We see context relevance improve a little bit improve quite a bit actually, from 0 to 0.55. But groundedness is the most, the one that sees a huge improvement. So if we zoom into the score, if we click into groundedness, we see the reasoning first. Okay, still giving more so like a similar answer, right? We can look at the answer here. FAST is similarity search library developed by Facebook AI Research. Slightly different, contains more relevant details. But more importantly, is that what it actually retrieve, right, behind the scene during those intermediate steps in a RAG system. So these stores, these are the context chunk that we retrieved. Compute Euclidean distance between all points and query vector. Aha, this is indeed the relevant piece of context that we are, hoping to find or find in the haystack, right? So, aha, we found the needle. Now, the statement here is just, we want to make sure each statement, there's only a single statement here. We want to make sure this statement is well supported. This is actually well supported by all the sources. So we get a fairly high score on the groundedness. And if we actually zoom in again to see the reasoning, you see there are actually 2 scores, and then being average, right? Have a score of 7, a score of 10. Finally, averaging it, we get a score of 8.5. The reason behind it is because the first one, supporting evidence, say Facebook AI similarity search. And then the statement actually contains more detail, which is not grounded, which is very interesting. This is, I'm like very deep in the weed here, but what I'm trying to say is that the statement sentence generated by the LLM actually contains more information than the grounding source of truth, or your custom data set. This is, we can consider like slightly hallucinatory, even though the answer is correct. This is the reason why our feedback function is giving it a score 7. It is very relevant. It is being supported, but not 100%. For example, like, how would you know it's a search library? How would you know it's not like an API, right? So that's the point I'm trying to make, like why it is not getting a perfect score of 100 point or 1 on groundedness score. So we see several good improvement. We can, zoom into context relevance. We will see very similar stuff here. But I want to kind of like take a step back and then say you can do a lot more in TruLens as well. You can, view different spans, check out the metadata. This should be directly tied to what you had in your LS document if you are looking at the retrieval chunk. I'm looking at the query here, so this is not from the Mongo LS. But if you look at the retrieval chunk, if we go into maybe this retrieve step, and then if we go into the details, we should be able to see vector search embedding. They're hard to find, but I'm sure it's somewhere around here. Yeah, sorry for this, is probably more or less for a screen, like size of the screen issue. But yeah, so you should be able to find the metadata file name being correct. I was trying to find in a needle here in a haystack. Hopefully I can find it. If not, I want to move forward to the next steps. Yeah, so we are having a better groundedness score, not so great on the context relevance front, on the high, as a whole. So the final one is just one mention, like how you could create your own feedback functions. This is a code that you need to create any type of feedback functions. Here, I'm just outputting one every time. So it can be a deterministic algorithm. It could be another LLM function, or it could be, another model that you develop yourself, or, some of the more scalable model TruEra might have offering. And then finally, you can just instrument your app with F custom function, and then you do the same thing. You just specify the feedback function name, you click run, and then you will have everything being populated in the UI. Or you could optionally extend existing feedback functions. We have, I lost count. We have countless built-in feedback functions like helpfulness, PII, like personal identifiable information detection. We have a particularly interesting one. We have adversarial detection to help you kind of like mitigate the jailbreaks that might have been injected into LLMs to guard against different type of malicious input, to help you, LLM to be, not so lenient to, sort of like a disclose information. But yeah, so that's the entirety of the notebook. I want to leave it on the open-ended note so that we can transition to the QA sessions if we still have some time. So we know the context relevance is still not perfect. I want to kind of sort of like open up to the audience, if I am allowed to say, like, is there any other way to improve that, right? The first one I'm just gonna throw it out there is maybe hybrid search will help, right? Here we are only using metadata filtering, so meaning we are looking at the fields of your document, right, of your imported documentations that we embed into the vector search space using MongoDB vector search index. But we could very well have a hybrid search approach. We have different weight, one weight on your vector search index, another weight on your metadata field, right? So that's just one of the way. And then some other ideas would be like swapping out different embedding models. There's a lot of like different advanced technique we can talk about. But I want to end here first so that we see if any unanswered question.
Why don't you go to the deck, Daniel? We're coming up to time, so
sure.
Let's just do the last couple of slides and take any final questions.
Definitely.
Let's move forward.
Okay. I saw the question about all these fancy patterns have been running locally on Windows. I'm using Windows, but I'm using WSL, so Windows Linux WS Linux subsystems. Yeah. And keep going. Yeah. So for more, Anupam, if you want to talk about it.
Yeah. This is a short 1-hour course that Jerry Liu and I did with Andrew Ng on deeplearning.ai. That provides a lot more context on the RAG triad, and it's very hands-on with notebooks. So please check that out if you haven't already. You'll get a lot more of the background related questions that were coming up in today's call. If you move forward, I guess we can, let's just end on this slide, and please feel free to check out TruLens. There's a lot of documentation, sample notebooks, and so on in the GitHub. It's an open source project with a very permissive MIT license, so feel free to use it in your day-to-day work. And then on MongoDB, Prakul, any final thoughts before we break?
Yeah, I think would be excited to have all of you try out. Any questions, reach out to on our community forums. But yeah, it's been super fun.
It's been fun to work together with Prakul and Daniel on this. I think to really scale up generative AI apps and get them to production, it's both important to have the right kind of data primitives, database primitives, and we saw some excellent elements of the MongoDB Atlas offering combined with strong evaluation, debugging, and monitoring capabilities, which is where we have focused at TruEra. So again, thank you everyone for your participation. We will wrap up here and stay connected with us. We have communities at TruLens and TruEra, and as well as MongoDB, so we can continue the conversation.
Yeah, thank you so much, Anupam and Daniel and TruEra team. It's been wonderful.
Thank you, Prakul.
Bye.
Thank you, Anupam.